Okay, we are continuing on here, chapter 16. So we start chapter 16, which is really our talk about thermodynamics. And when we deal with thermodynamics, it really is sort of asking a lot of times sort of the questions of, will a reaction take place? And again, sometimes that is what is referred to as being spontaneous. And as we talked about last time, spontaneous really in this sort of context doesn't really have anything to do with how fast or slow a reaction takes place. That obviously, as we talked about, is sort of the kinetics of a reaction like we did at the very first chapter. But again, spontaneous basically just means that under those conditions, all the conditions are correct for this reaction to take place. Again, it may take place really fast, it may take place really slow, but it will take place. And again, that's sort of what the spontaneous sort of refers to. Some common thermodynamic values, some from your past as well, which is our delta H, which is our enthalpy. The enthalpy is the heat of a reaction. And we oftentimes will use sort of the sign of delta H to help us determine if a reaction is exothermic or endothermic. And again, if you have a negative delta H, that reaction is exothermic, which means heat and energy is released. And obviously, if you have a delta H value that is positive, that is going to be endothermic, which means heat and energy is absorbed. Now, one of the things we talked about was the idea that, although an exothermic reaction sort of favors spontaneity, it doesn't necessarily guarantee that a endothermic reaction wouldn't be spontaneous. So again, just like the melting of an ice cube is a spontaneous process, and that's an endothermic process, a spontaneous process can be exothermic or endothermic. So sometimes we need to look at some other sort of thermodynamic properties to help us decide. And that's where we talked about entropy. And entropy is sometimes usually abbreviated as delta S, which is the change in the entropy. And that really is sort of the amount of disorder there is. So in terms of delta S, a couple of different things between H and S. First off, H in terms of units are typically in kilojoules. S is typically in joules. So there is going to be an equation later on in this chapter where we kind of use both of those values together. So you always want to watch your units there. Otherwise, you will be off by a factor of 1,000. But a lot of things we think negative as sort of things happening and stuff like that. And actually with delta S, the value becomes more positive when there increase in disorder. So an increase in disorder will basically result in a delta S that will be more positive. And the opposite is true. If you end up with a delta S that's a more negative value, you're seeing the disorder decrease, which by the same token would mean that you're having a lot more order that's happening in that. We talked about the idea that, changes of state are a very simple way to sort of think about order and disorder. Obviously, as you go from the solid state, which is a very ordered sort of situation, especially, for example, if you're dealing with an ionic solid, everybody's arranged in a very, very repeatable type order. And that has a very more negative delta S than as you go to liquid, where everybody's moving around a little bit more. So there's a little bit more disorder that's happening, to the gas phase where everybody breaks apart and basically is flying around, creating a lot of disorder. So the gas phase would have a lot more positive of a delta S value than our sort of solid state. Any questions on the stuff we talked about last time? We also saw that, one way that entropy is related is through what is sometimes referred to as microstates. And microstates are, again, just sort of different ways that you could accomplish something. And again, I think we had circles and boxes, if I'm not mistaken. So If we want to put all 4 circles in like one box, there's only really one way to do that. And again, if you just kind of go into this equation with 1 for your W, that is going to zero out. Obviously, your entropy value will give you a much smaller one, as opposed to, I think there was one where there's like 6 different possibilities of sort of putting 2 circles in each box and stuff like that. That obviously gives you a much larger, more positive entropy value that you would get there. K in this case is what is referred to as the Boltzmann's constant, which I think was on that slide as well. Any questions on any of that stuff there? Okay, so I think we left off with this example. So for each of these processes, take a minute or so here and decide, is the entropy of the system changing? Or how does the entropy of the system change? Is it sort of increasing, decreasing? Would you expect a positive or negative delta S for each of these situations that occur? So take a couple minutes to see what you come up with. Condensing water vapor. So condensation is the process where we're going from gas back to liquid, I still think. And that means we're going from a situation where we're in the gas phase, where there's a lot of things flying around, a lot of disorder, to in the liquid state where they're not flying around, obviously, and come together a little bit more to a more ordered situation. So the amount of order increases, or if you like the opposite of that, the amount of disorder decreases, right? In both of those cases, what that basically would mean is we would actually expect a delta S to be a negative number. Again, the more order that you create, the delta S there would be a negative or less than 0, basically. Any questions on that one there? Forming a sucrose crystal from a supersaturated solution. So a crystal would be a solid type situation, and a crystal is usually a pretty perfect crystal. So that obviously is going to create a lot of order. And that also should mean that we would expect our delta S value to be less than 0 or a negative value because of that. Again, crystal is basically a solid sort of structure that comes together. For C, we're heating hydrogen gas from 60 to 80. So we have hydrogen gas. When we heat the temperature, I would expect this guy to start flying around a lot faster. That then should increase the disorder in this case. And that would then mean that we're actually going to end up being a delta S value that is greater than 0 or positive in that particular case. And lastly, sublimation there, dry ice. That is the process where you go from solid to gas, directly skipping liquid along the way there. And that means that the entropy here should be negative or positive. Should be positive. That obviously is going to increase the amount of disorder. Obviously, you're going from something in the solid state to something in the gas state where everybody's flying around. And obviously it would create a lot more disorder, resulting in a positive delta S value. Any questions on any of those there? So let's talk a little bit more about entropy. Entropy is a state function. And perhaps you remember talking about state functions when you talked about probably enthalpy and energy in Chem 50. But just in case you didn't, state functions are basically functions which it really doesn't matter how you got there. It just matters where you ended up and where you started. So if we look at these two guys here, our hikers, they both really do possess the same potential energy because they're standing basically in the same location at this point. The kind of blue hiker took the more direct route up the mountain. The red hiker took the scenic route up the mountain. There's always that option when you're driving, take the scenic drive or the more direct route. But in the end, what really is important in terms of potential energy is sort of where they both ended and really where they both started. And that's why in a lot of things like entropy, also like enthalpy, energy, pressure, a lot of times you calculate those things by basically taking final minus initial sort of conditions, right? Final temperature minus initial temperature. When we talk about a reaction, right? Our reactants and our products are final guys are our products, right? And our initial conditions are our reactants. And that's why when you calculate, say, something like enthalpy that you probably learned, you take the delta H of the reaction is the delta H of your products, right? Minus the delta H of your reactants. That's basically your final condition minus your initial condition in terms of the chemical reaction. So entropy is also a state function, and that also is one of the ways, as we'll see here in just a second, that we actually do calculate something like entropy, is you take the products minus the reactants. Much like delta H and delta S values and delta G that we'll talk about in this chapter, there are a table in the back of your book there. I think that's where that table comes from, where you could actually look up these values for H, S, and G, which is Gibbs free energy. A couple of things that are a little bit different in terms of the entropy values versus, say, the enthalpy delta H values is, as I mentioned before, one of the major differences is the units. Again, joules here typically with our S, and obviously, as I mentioned earlier, kilojoules usually when you kind of look up that guy. In addition, typically our delta S values are all positive when you look it up in the table. And unlike delta H, if you have a delta H, you want to look up the delta H of formation for something like O2, the answer would be, it would be 0 kilojoules. So for enthalpy delta H, anything in a standard state that's uncombined, typically when you look it up on a table, it will be 0. But when you look up those things on a table for entropy, you will actually find values for those guys. So things like O2, H2, things that are in their natural state, you'll actually still find values for. So that's something that's really different as well. So the other important thing in terms of all thermodynamic tables is not only to look up the substance, but you want to make sure you also get it in the right phase. So that's a very common mistake people make when they go to those tables and look things up. They just take the first water is a very common one people screw up on. They take the first water in the list. Maybe it's actually in the gas state, which is not what you need, right? So you want to always make sure, again, not only what you need in terms of those tables, but it's in the right phase so you get the right values. So the first law of thermodynamics really is all of that energy stuff that you learned about enthalpy, the conservation of energy, right? We don't create nor destroy energy along the way, but we can transfer energy. And one very simple sort of aspect of energy that really works well is the idea of, obviously, there's a system and a surroundings. And basically, we think of energy being transferred sort of perfectly, which means, for example, if the system loses a certain amount of energy, the surroundings should pick up the exact same amount of energy, and vice versa. The surroundings should actually lose some energy. The system, in that case, would pick up the same amount of energy. The only difference is really the sign, right? So anything that's releasing energy or giving up energy, again, it would be a negative sign for it in terms of the value for energy. And anything that's absorbing it would be the exact same number, but just a positive value for it. The second law of thermodynamics, which is sort of what we're dealing with here with entropy, is that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So we can use entropy to help us decide whether or not a reaction will be spontaneous. But in order to do that, we do have to calculate one thing, which is actually the entropy of the universe. So we have to take care and calculate the entropy of the universe. And if it is greater than 0 or a positive number, then that reaction will be spontaneous. And obviously, if it's less than 0 or a negative number, then it will be a non-spontaneous process. To calculate the universe entropy, we need to calculate two things. One is the delta S of the system, and the other one is the delta S of the surroundings. If we happen to calculate the delta S of the universe, and it does equal 0, then it is an equilibrium process. Basically, at an equilibrium process, nothing much is changing, right? Because everything is kind of going back and forth at the same rate. Everything remains sort of the same in terms of where everything's at that point. Any questions on that there? All right. That was a heck of a lecture today, I think. All right, we will lay it up here today. A couple of reminders.